Okay, hello everybody, and today we'll be talking about this question. Is the ABC formula a derivative? And it might not be obvious what I mean by this question, but it will be in a moment when I explain everything in detail. So let's first of all recall what the ABC formula actually is. So when we have a quadratic equation of the form ax squared plus bx plus c, and we want to know its zeros, so when this is equal to 0, it turns out that x is going to be equal to negative b plus or minus, so there are two solutions, the square root of b squared minus 4ac, all divided by 2a. So notice here that a cannot be equal to 0, because then we'll be dividing by 0 down here. And that makes sense because when a is 0, this isn't a quadratic equation. But let's make a equal to 0 and then solve for x. So if bx plus c is equal to 0, then moving the c to the other side and dividing by b yields x is equal to negative c all divided by b. So keep those two in mind. And now we're going to take a random parabola. So a parabola is in fact a quadratic formula. So this is a random one, it has two zeros. And now we're going to let a go to 0. So if you plot this on decimals, for example, you'll see that when a is going to 0, maybe here we have a second iteration, your parabola is going to look something like this. And with a 0 still down here and a 0 up here, and when you make a equals 0, your parabola, it's not a parabola actually anymore, it looks like this. Then it's a straight line. So it looks like one of these zeros is somehow tending towards infinity, and it's not actually present when a equals 0. And the other solution kind of stays at the same spot. So it looks like this point is actually the limit of all these points. So this way we can make a conjecture that the limit of the ABC formula, so let's write it down, the limit of the ABC formula when a goes to 0, negative b, well, we don't actually know, it was one solution, so we don't know whether or not to take the plus or the negative one. The square root of b squared minus 4ac all over 2a. It kind of looks like this would be equal to negative c over b, because as we saw earlier, when you let a go to 0, one of these two solutions looks to go towards negative c over b. So going toward is a formal way of stating that is saying that the limit is equal to that. But these two things don't actually look like each other. So that's kind of a problem here. So there are actually two ways of showing this, at least two ways. One is by rationalizing the numerator, but I've got a neater trick. It's a little bit longer, but we'll be getting some nice results out of it. So let's first of all define S. S is going to be the sign of b. So if b is positive, we can write S like this. It's going to be 1 if b is positive. It's going to be negative 1 if b is negative. And what do we do when S is equal to 0? Well, that doesn't really matter. We don't care about b equals 0, because then we will be dividing by 0 down here. And when we have the equation ax squared plus bx plus c, and we make a and b both 0, then there won't be any solutions except for if c equals 0 when there are infinite solutions. So that's not actually an interesting case. Well, and this is the sign of b, and there are other ways to represent it. It's actually also equal to, so this was s, it's also equal to b over the absolute value of b, and the absolute value of b is always positive, so if b equals the absolute value of b, this is 1, and if b is negative, you see this will yield -1. And this is actually also equal to the absolute value of b over b, because 1 and -1 are, and when you do 1, when you invert them, you'll get the number back. And 1 over 1 equals 1, and 1 over -1 equals -1. So that's nice. And now my claim is that the limit when a goes to 0 of -b plus s times the square root of b squared minus 4ac all over 2a will be equal to -c over b. And we're going to show it right now. So to answer the question whether or not we should take the positive or the negative version of the solution, that depends on whether b is positive or negative. So let's work out this limit. First of all, I'm going to swap those two. So this is equal to the limit when a goes to 0 of the sine of b times the square root of b minus 4ac minus b, and then over 2 both, and then the whole thing over a. So I'm going to write it like this. And then notice that we can write this as the limit when a goes to 0 of the first part. I'm going to leave exactly the same, minus 4ac all over 2. But then we're going to replace this with the sine of b times the square root of b squared all over 2, and then all of this divided by a. So let's talk our way through that. B is equal to the sine of b times the square root of b squared. There are different ways of seeing this, and this thing is always, this is a positive version of b always, and by multiplying it by the sine of b, we're giving it its sign back in a way. Another way of viewing this is that the square root of b squared actually is the absolute value of b. So by our identity up here, we see that s times the absolute value of b will give us b back. So this is true. So now these two things look kind of similar, and I'm going to introduce a function to clarify that. So f of x will be equal to sine of b square root of b squared minus 4 times c times x. And we see that this part up here is going to be f of a, and this part up here is f of 0. So that's nice. So we can write this as the limit when a goes to 0 of f of a, but I'm going to write it as f of a plus 0 minus f of 0 all divided by a. And of course this should have been a over 2 down here. So that's nice, and I guess some of you will remember this limit. And this is actually the derivative of f at 0. Yeah, because remember the derivative of a function is defined when we want to calculate the derivative of f at a point d. It's going to be equal to the limit when h goes to 0 of f of t plus h minus f of t over h. And well, here a is replaced with h and d is equal to 0. So actually what we are calculating is the derivative of a at 0, this thing up here. And we can quite easily calculate the derivative of f. So the derivative of f at a random point x is going to be, well, first of all we have s over 2. That's just a constant, it stays the same. Then we have the derivative of, and we have to use the chain rule, or the chain rule as Dr. Payam likes to call it. We have 1 over 2 times the square root of b squared minus 4cx. And then, oh, it's kind of out of screen, and then we multiply it all by the derivative of the inside, which is negative 4c, so negative 4c on top. And now when we evaluate this at 0, we get that negative, the derivative of f at 0 is going to be equal to, well, first of all we have s over 2. Then we've got still negative 4c on top. And we've got on the bottom, we've got 2 times b squared. And of course all inside of a square root. And then we see that this 2, this 4 and this 2 all cancel each other out. So we're left with s times c over the square root of b squared. And the square root of b squared is the absolute value of b, and s was equal to the sine of b. So we're going to write it as, there were 2 ways to write it. Let's remember them, those 2 ways. And now we're going to use this version. So previous we used this version, now we're going to use this version. And we see that this is equal to the absolute value of b times c over b, and then all of this over the absolute value of b. Of course still with this negative sign down here. I forgot that one. We see those 2 cancel out and we get exactly negative c over b, which is where we want it to end. So that's really nice, and it's nice in different ways. So first of all, it's nice because we use the definition of a derivative the other way around. And mostly when you calculate a derivative, you're going to use the definition of a limit, then calculate the limit, and then find out what the derivative is. Now we did it the opposite way, so that's nice. And the other way, this is nice, is because it makes sense, of course. It was what we wanted to show, what we conjectured. And there's another way, so let's get back to the question we asked at the very beginning. Is the ABC formula a derivative? Well, it actually isn't, but it's kind of going in that direction, because what we showed is that one of the solutions of a quadratic equation was equal to, without the limit now, f of a minus f of 0 all over a, where this function f was being equal to f of x equals s times the square root of b squared minus 4cx, and then all divided by 2. And of course this is the slope of this function between these 2 points x equals 0 and x equals a. Yeah, so this actually becomes a slope of this function between 2 points, but actually becomes a limit if we let those 2 points go to 0. So this function is really related to this quadratic equation in the way that one of the solutions of the quadratic equation, ax squared plus bx plus c, is equal to the slope of these 2 points of this function. So that's very nice, and that's what I wanted to show you. Actually, I derived this all myself, so I'm very excited about it. I want to tell you one more thing, which is that well, this where this way we go from the solution to a quadratic equation to a linear equation. There actually also is a equation to solve a cubic equation. So I tried to generalize this construction with such a function f, but it turned out that wasn't easy. I got hopelessly stuck. So I wondered if there is such a generalization possible. So if you guys come up with such a thing, tell me in the comments. Because I'm really excited about this function and the way this all works. So maybe we can extend it a little bit further. So that's it for today, and I wish you guys all a lot of math.